All right, so thank you for coming. I think it's just a few of us. I think we can keep it informal. I mean, if you have questions, just let me know, and I think we can clarify. So today's topic, we're going to talk about learning user preferences for multimodal data. These are the topic of research that our group is focusing on right now. So I and Maxim, we come from the same group, and we're going to talk about some of the things that we are doing. This is still work in progress. So if you are interested, let us know. And I think there are some things that we continue to work on. That means now we come from Singapore Management University. So just in case you are wondering where Singapore is, so that's probably where we are, right? Somewhere there. And Singapore, we are a long way. We are right at the equator. And this is actually aligned very close to 0 latitude, so which means that it's warm. It's we are this morning, right? So we are 32. This is a plus, not minus. This is plus 32. St. Petersburg now is about minus 15, so it's a big difference of the temperature. And this temperature is not just this time of the year, is all the time. So whether it's January, March, June, December, it's always the same. Now, if you come to Singapore as a tourist, so this is one of the iconic buildings. I think sometimes when you Google or Yandex Singapore, right, so you might get an image like this. This is like the casino building. It's a very popular place called Marina Bay Sands. Now, but if you are locals, most of the time this is what you see, because Singapore, the whole country is just one city, 5 million people. So that's very crowded, very dense. So we live in like tall, high-rise buildings. Now, the Singapore Management University, so we are one of the 4 research universities in Singapore. Now, we are unique in the sense that we are located in the downtown of Singapore. It's right in the middle of the city. Now, we are established in the year of 2000, so we've been around for about 17, 18 years. And the number of students are about 10,000. 20% of them are postgraduates. So these are like masters, and probably about 5% or so are PhDs. All right, so we actually bring a souvenir, and later we are going to give it away. Just we're going to ask a question at the end, and to one of you. All right, so now we are from the Management University, but our school is School of Information Systems. Essentially, you can think of it as computer science department, but within a management university. So meaning that we have a lot of the computer science disciplines, but not the hardware things. We are more focused on computer science disciplines that are related to somehow to business problems. So that's like data science, cybersecurity, information systems and management. So that's applying computing to business. Intelligent systems and optimization. This is like AI kind of problems. And software and cyber-physical systems. This is dealing with software engineering as well as things like sensor networks, Internet of Things, and things that deal with device computing. So the group that we come from is web mining group, meaning that we focus on data mining and machine learning, but oriented towards web data that you can get from the web. These are things that generally reveal something about the behaviors and preferences of users, and that's where we are focusing on. This is our group. That's myself, and that's Maxim doing one of the group outings. Now, today we are going to talk about these user preferences for multimodal data. We're going to come to the multimodal part later, but we're just going to motivate a little bit. Why is it that we focus on user preferences? And one of the key motivation is the fact that now, whatever we do, we have a lot of options. We have a lot of choices. Now, this is an example. I'm going to use examples from Amazon because that's what we are familiar with in Singapore. Now, let's say at some point I go to Amazon, and if I'm looking for men's shoes, so they're going to be like 135,000 results. So we can't possibly look at every single one of them. Now, if you are looking for iPhone case, there are 200,000 results. If you're looking for ebooks, then it's like 1.6 million. So that means that there needs to be a way for us to narrow down the possibilities, and most of the time that means that we need some form of recommendation, meaning learning about what the user prefers so that I can show every user a different set of results. This is especially because most of us now are doing things on mobile phones, meaning there are not a lot of real estate on the screen, and that makes it all the more important that we need to get to the few options that the users are more likely to like. Now, this is like an example for Amazon. So based on your browsing history, for example, then it's going to choose which of the headphones to show you. This was some time ago when I was trying to find earphones for exercises. So now, one of the problems that give rise to a lot of work on recommendation systems is the competition, which is Netflix price. Netflix is a US company that was doing video on demand. And at some point, they give away $1 million as long as you can beat their recommendation system by about 10%. And after a year-long competition, international competitions, in the end, there is a group that won the competition, but it took them a long time to actually beat this 10%. And even then, this group is not just one team, it's actually a merger of multiple teams, because it's a very difficult problem to actually come across and to cross that boundary. So yeah, so they went away with $1 million. Now, at that point of time, a lot of the technology behind recommendation systems is something that is called matrix factorization. So the basic idea is to look at the data, and most of them are ratings data, meaning people rate movies 1, 2, 3, 4, 5, and you represent that as a matrix form. And inside the matrix, this is users, this is movies. So then a particular element is going to be the rating that a user assigns to a movie. Now, this matrix is, a lot of it is empty. That means that you only observe very few values. A lot of them don't have any value. So to predict the missing values, what a lot of the methods are based on is to decompose the matrix into latent factors. So you imagine there are going to be factors for users, factors for movies, to the extent that you can make a future prediction by multiplying the factor for the user by factor for the movie. So for example, if you want to know what is the rating by user 1 on movie 3, so then you take the factor for user 1 and the factor for movie 3 and you multiply them together, and then you get a prediction. So now the latent factors are learned from the data by optimizing this particular equation, where we are basically trying to identify the factor that will minimize the error in terms of the prediction. So this is a prediction and this is observed rating, and we are looking at the latent factors that will approximate the rating as much as possible. Now, this is relatively successful, but it's still, so over time people realize that the accuracy gain is getting smaller and smaller, so better algorithms don't solve the problem. So that means we need to go beyond just better algorithms to essentially better data. And one of the reasons why that is the problem is exactly because of the sparsity. And the notion of sparsity meaning that we don't have a lot of data for individual users, and there are always new items. So whenever there is a new item that comes to the system, we don't know anything about that item, so then we can't really make predictions for that new item, because we are relying on ratings, and before there were ratings, we cannot do any prediction. So then to go, the proposal then is to go beyond the ratings, meaning not just try to build better algorithms, but we go wider and see what other data we can use to learn about user preferences. And the way that we are doing that essentially is to do something that we call multimodal preferences, and the idea is to look at different modalities of data. So it turns out that users on the web, they indicate their preferences in many different ways, not just through the ratings. In some cases, they write reviews. So this is text, and the text is rich in the sense that they describe a lot in terms of what they like or dislike. And at the same time, the individual products or items that we want to learn about, they have some description in terms of, these are like metadata. This could be product attributes. This could be some product description, synopsis, and so on. Now, there are also images. So increasingly, people post images on the web to indicate what they like preferences, like Instagram, and people just keep posting photos and you kind of get a sense of what kind of a person they are. Now, finally, there is also the social network. And here the idea is that a lot of times you are our people. People generally tend to hang around with other people who are similar to themselves. So meaning that if I don't know about someone, but I know something about their friends, I can infer something about the person just based on what I know about their friends. Now, this is essentially the key thrust that we are doing, which is to look at the different modalities and see whether we can extract the preference signals from them. And that's essentially what we are going to do in this project. Now, this project is called preferred.ai, and this is, it stands for Preferences and Recommendations from Data and AI. So the project itself, it aims to build an end-to-end recommendation framework, meaning that it's end-to-end coming from the source of the data all the way to the actual recommendation applications. And the key engines, there are essentially three main parts to them. So the first part is what we call data infrastructure and representation learning. This is something to do with collecting the data and, more importantly, extracting features from the data that reveal something about the user preferences. Now, the second part is the algorithm to do the recommendations. These are the algorithms that learn something about the user preferences and then try to personalize the recommendations. And finally, the final component is what we call a recommendation retrieval. This is essentially a personalized search engine for products. And here the key challenge is how do we return the results in a very short time? Because you realize that we are so used to using search engines that return results almost instantly. You put in a keyword and then within a second you get a results. Now, but for recommendations, the same keyword, you want to return different results to different people. So that makes it complicated because now you cannot maintain a different index for a different person because then they will be expensive in terms of storage. And yet we cannot just maintain a single index because then I cannot personalize it to different people. So then there must be new data structures that knows how to personalize things while still keeping things in a compact form. Now, these are the different components, but here what we are focusing on today is the notion of multi-modality. Essentially, the focus is on different types of data and how do we extract preferences. And now we're going to talk about three things today. Something about images, something about text, and finally something about social networks. Okay, so let's start from images. And the basic idea here is to look at whether we can understand something about likes and dislikes based on the images that people post online. And we're going to start with examples from online reviews. Now, this is from Yelp. Yelp is a service in the United States for restaurant reviews. So the idea is that people visit a restaurant, they write a review, and increasingly, they are posting photos together with the reviews as part of the review. And this is common nowadays because, you know, we all carry mobile phones, right? So we may go to a restaurant, we eat something, we take pictures, and then we include it as part of the review. Now, if you look at these numbers, for example, this is, by the way, a Japanese restaurant selling ramen. Now, this is a restaurant in New York City. It has 8,500 reviews. Now, there are 7,400 images. So there are almost as many images as there are review texts. Now, in the past, when people look at these reviews, the focus is on learning sentiment from the text. So that means they look at the text itself and they will try to figure out is it positive or negative. Now, this is an example. So Akamaru Modern with Kakuni. So this is a ramen dish. Ramen is like a Japanese noodle soup. And here, if we read this sentence, we probably can tell that this is a positive sentiment because there are words like best and so on. Now, the problem that we are addressing in this particular work is what we call visual sentiment analysis. And the idea is to look at a picture and to identify what sentiment is this. This is like a small kid, right? And he's drinking all of the bowl. And we want to know, is it positive or negative? And this is probably positive from our point of view. Now, the method that we are building this on is something called convolutional neural networks. So I'm just going to go through a little bit about some of the basic things about the methodology. Now, neural network is a machine learning model that tries to simulate the way that a human brain works, but not very closely, right? It's very loosely. Now, the basic idea is simply that this is a single neuron, and here there are inputs. The inputs are things that come from the data, and the neuron is going to combine the inputs in a certain way, and the more important input is given a higher weight. So here there are different weights for different inputs. And finally, we aggregate them and output a value. Now, when we output a value, most of the time we are going to transform it in a certain way, and there are different functions for the transformations. So for example, in a sigmoid function, it will be transformed to a value between 0 to 1, because most of the time we want to model probabilities. In the time function, we are going to transform it from -1 to 1. And this is a rectified linear unit, or ReLU, which is to avoid the negative elements by putting a threshold of 0. Anytime there is negative, it's just going to be set to 0. Now, why neural network uses this kind of transformation functions? Well, one of the things is to maintain some non-linearity in the model. Another thing is that it helps to balance things out, because by restraining the ranges for different neurons, we can then combine different neurons so that one doesn't dominate another one. And in this case, this is a more complex model that has multiple neurons. So this is just one of them. So there are multiple inputs. It goes to, in this case, one hidden layer, and these are different neurons. And finally, there are multiple outputs. Now, this is a simple model, but you can imagine that there can be many more inputs, many more neurons in the hidden layer, and it allows you to model different kinds of functions. In fact, now the trend is to do deep neural networks, where you put in multiple hidden layers, and in that way, you basically compose a function out of a simpler function. And as you get to a higher and higher level, it becomes a more and more abstract function that is a combination of the earlier functions. Now, but when we talk about images, images are a special kind of data. It's a kind of data where there is some information in the way that the pixels are ordered. Meaning that if I show you an image and I randomize the pixels, you will lose all the information, because all the information is in how the pixels are arranged in terms of the neighboring. So in that sense, a lot of the work that are looking at images are based on something that is called a convolutional neural network. Now, this is a kind of neural network that tries to maintain the idea of a neighborhood within the input data. So for example, in this case, this is an input image. Here there are 3 layers. That's like the RGB, red, green, blue kind of a representation. And the idea is that instead of looking at the data 1 pixel at a time, we are going to look at 1 window at a time. Because in this case, you take a small window, and within a small window, we can probably try to guess what kind of object might be within that window. In the simplest kind of window, it would just be like a line or a circle or some simple shapes. Now, this process of learning from a window and trying to detect some features that are based on the spatial forms of the images is something that is called convolution. And the basic idea of a convolution is to imagine that there is a filter. And this is a 2D filter. And the filter is looking for a certain kind of a visual shape or visual feature. So, for example, let's say a filter could be looking for a line that has a certain shape. For example, like it could be like a crossing or... now, this filter then is going to pass over the image. So let's imagine that the green thing is an image. And so we take this filter and we take the filter and basically pass over the images systematically. And in that way, we are going to look at, we are going to multiply the filter value against the pixel values and sum them up, and we are going to get another value. Now, the thinking is that if there is some high value in a certain part of the image, it means that the filter has detected a special feature within that locality. Now, this convolution, you can do multiple of them. So here, in this case, like every layer is a convolutional filter. So in this case, you have many filters that make up a block. And by transforming this into the convolution, you get essentially a different image. So here, there is RGB, but by the time you come to here, you can have many more filters. So essentially, your image has many features. Now, then there is something called pooling, and the pooling is a way to reduce the dimensionality of the image. Because at the end of the day, you may be looking at 1 million pixels, but really the features that you're looking for are certain shapes. Meaning that, for example, you're just looking for faces or circles, and that allows us to simplify the data so that you get a much smaller dimension. This simplifies the model, you have fewer parameters, And at the same time, it makes it more generalizable because it doesn't try to fit every single pixel. Now, when we do that, and this is the notion of deep learning, is that you can then stack up multiple layers of convolution and multiple layers of pooling, so that over time, the multiple layers of convolution, what you're doing is to detect different abstractions of the visual images. So the first convolution might be looking for lines. The second layer convolution, for example, might be looking for simple shapes like circles, triangles. The next level of convolution might be looking for more complex objects like faces, which is composed of many different kinds of shapes, and so on. Now, at the end of it, you get a what we call a fully connected layer, which is essentially a normal neural network that tries to do the classification. Now, in this particular example, we might be trying to detect an object, whether there's a car, a truck, a van, and so on. Now, but for this particular problem, what we are looking for is the sentiment. And so this is what we call visual sentiment convolutional neural network. And the final classes that we try to learn are just positive and negative. That's why the final layer only has 2 nodes. Now, this is based on an architecture that is called AlexNet, which was used initially for object detection. But we modify it and adapt it for visual sentiment analysis. Now, one of the key ways that this model is architected, so of course, one is that you have these multiple convolutional layers. In fact, there are 5 of them, and then 2 fully connected layers, and there are 2 streams, because in some sense, you can parallelize the model. If you have multiple GPUs, for example, then you can fit this into one GPU, you can fit this into another GPU, and then you can combine it at the end. And that probably helps to parallelize the computation and makes it more efficient. Now, if we were to run this on a data that we get from Yelp, which is a restaurant data set, and this is data that we get from restaurant reviews. So we go to these 7 cities in the US to collect the data, and we will predict 2 classes. So the ratings go from 1 to 5. So 1, 2, 3, 4, 5. So we are going to assume that 1 and 2 means it's negative. 4 and 5 is positive. So we ignore the 3 because the 3s are ambiguous. Now, this is a balanced data set. So that means there is equal number of positive and negative images. So a random classifier is going to get 50% accuracy. Now, if we fit it into a naive-Bayes classifier, we get about 0.54. Point-wise, meaning that we just look at the accuracy of the class. A different metric is pairwise accuracy, which means that we gave the model 2 images, one positive and negative, and then we asked them to compare, like which one is more positive. So that's an easier task, so that's why the number is a little bit higher. So here we get a little bit of a performance improvement over the naive-Bayes, but not by very much. Later we're going to talk a little bit about how to improve it further. But the first thing is that I would like to show you some of the examples of the sentiments that we get from the images. Now, these are the positive sentiment images. That means that these are images that the model classified to be positive. So one, so the way that the model works is to detect visual shapes and look at the correlation between the shapes and the ratings. So if certain shapes are generally correlated with positive, then we are going to detect it as positive. If certain shapes are correlated with negative, then we are going to detect it as negative. So it turns out that a lot of times, whenever we see pictures of drinks within the reviews, they tend to be positive. Now, when you see a face, like one face, most of the time it's like people celebrating something or views. And these tend to be possibly high-end restaurants, right? You go to very nice hotels, you go to the top of the building, and then people capture the pictures. And group pictures. Group pictures tend to be positive because like people, some people are taking pictures together, probably that's a happy occasion. Now, there are also examples of negative sentiment pictures, right? So these are like restrooms. I mean, when people complain about something, this is one of the things that they complain about. When they detect pictures of flooring patterns, this probably to complain something about, I don't know, it could be like the cleanliness or the hygiene or something. Now, the bills. So when people write a review and they take a picture of the bill, that tends to be negative. And of course, you know, like this kind of surfaces where there are white surface and some black dots, it's probably negative. Now, but the interesting thing is that we realize that different restaurants actually associate different visual features with different sentiment, meaning it's not all the same. Now, I will give you an example. So earlier on, we saw like a lot of faces, right? So group pictures tend to be positive, but it turns out that for some restaurants, a lot of, if you see a lot of faces, it tends to be negative. And for example, right, we look at the data, and for example, what happens is that it could be that it's a long queue, and the restaurant always has a long queue, and when people take a picture of that queue, the model detects faces, and then it starts to think that it's actually negative. So it confuses the model, and that's part of the problem with the sentiment analysis, because there is some subjectivity in the problem that you cannot just use one model for everything. So then what we go on to do then is to try to make this, to allow it to specialize for certain restaurants. So meaning that you still have one model that shares most of the parameters across many restaurants, but for specific restaurants, you allow some number of parameters to be specific to only that restaurant. So in case that it encodes some feature that are unique to that restaurant. Now, but the question is that where do we do that? Because you can do that at any of the convolutional layer, or you can even do that at the classification layer itself. So we tried these different levels of abstraction. Now, what we do is that, okay, if you take a convolutional layer, now you take a slice of that, and a small slice will be specialized to one restaurant. So that means it's a specific parameter to that restaurant. The rest are going to be shared across all of them. Now, if you do that, it turns out that depending on where you introduce these specializations, the performance improves further. And it turns out that the later you introduce it, the better the improvement. Now, it makes sense because what happens at the early stages, these are like very, very basic features, like lines and so on. By the time you come to the final stages, this tends to be more complex objects, so like faces and so on. These are probably something that is detected later. Now, in fact, if you go all the way to the end, this is when we look at a fully connected layer and we reserve some parameters for each specific restaurant, we get the best performance, but it's still around 62% point-wise and 68% pairwise. Now, we can either specialize at the item space or at the users, because it could be that different users also have their own specific preferences. And if you do it at the user level, it turns out the performance is actually better, which is around 65%, 74%, and the pairwise. Now, this is what we uncovered so far about images. Later on, we did further work where we look at, if you compare, for example, between images and text, text is still more informative. Because people say complex things within text, and for text the accuracies are going to be a lot higher than this one. But it turns out that sometimes images and text together can be helpful. In some sense, if you look at a review, right, the review has a lot of text explanations, and the images that they include as part of the review tend to put highlights on the important parts of the review. So, for example, they may take they may write something about a long queue, and they will take a picture to emphasize that. And so by detecting the visual features from the image, you can then highlight that the most important part of the text is actually the part where they talk about the thing. So yes.
Could you please tell more about this issue with faces? So if you, on some pictures there are faces because they are inside the restaurant, and some other faces are from this line of queue. But the faces that are inside the restaurant, they are presumably more happy than
right.
So can you just do some not just face detection, but
emotion recognition. You mean emotion recognition?
Right.
Oh, emotion. Oh, I see. Okay. Now, well, in theory you can. That means, but it's going to be a different kind of supervision. So that means that in this case, you first have to, It's actually a lot more complex than that, because if you really want to do that, there are multiple layer levels. So first of all, you need to detect whether there is a face. That's like a face detection algorithm. Then once you capture the face, then you try to detect the emotion, right? And because there are multiple faces, then you have to gather the emotions. You have to aggregate them into an overall thing. So in theory, you can do that. We haven't done that because this is like more like a general purpose model. So it's not specific only to the faces. It could be like any part of the any part of the restaurant. And right now, I think the basic thing that we're learning essentially is the correlation between the visual features and the sentiment. And it's just that if most of the time you see face means positive, then the model will think that the face indicates positive. It could be that the face actually is sad. Yeah, but yeah, I guess I think if you put more, if you make it more specific, like if it is based on facial emotion recognition, then it's going to probably be more accurate for those kind of facial features, but then it may not work for non-facial images. Yeah. Now, at this point of time, I'm going to pass it to Maxim, because we are going to have some discussions as well about the review text.
All right, so I'm going to discuss a little bit the text and the reviews, and the question we're going to answer is which camera is better. And we're going to answer it by looking at the reviews. Well, actually, personally, when I try to pick the complicated electronic product and I don't know what is it about, which product to choose, I go online, look at the different reviews and understand what people do say that, like this camera is good or that camera is better. And by looking at a lot of reviews, I kind of try to understand what should I buy. Well, in this work, we are going to look at this one particular example of the sentences, which are comparative sentences. Like here, compared to the Canon 7D, the Nikon D300S gives sharper pictures, which indicates that one product is actually better than another. And we are going after these sentences that we can find probably a lot online, on Yandex Market for Russian language, on Amazon, which is an example here, or probably on social networks like Twitter or Facebook. Well, sometimes people do say like, I bought this camera and it's really awesome and it's much better than my previous camera. So we are going to process all these kind of sentences. This is a little bit different from the sentiment analysis. Why it is? Where the sentiment analysis is essentially to classify a sentence by a positive, whether it indicates the positive affection or negative affection. But if you tell me, for example, that 7D is good, and I'll tell you that D300S is good, we still don't know which camera is better. So we don't have this experience to compare these two cameras. And this is probably going to solve the indicator, give us the more accurate signal about comparing the cameras. All right, so given a set of comparative sentences, a comparative corpus, we are going to answer two questions, like how to interpret each individual sentence and how to rank all the products with respect to these sentences. Well, essentially to answer the question, which product should you buy, which camera should you buy? And these are two different problems. You can try to solve one by classifying, by trying to interpret the sentence individually using the classification algorithm, and then try to rank the products using something like PageRank or competition models. I'm going to prove you that considering these two problems together actually can help us to solve both problems in a better way by giving this example. So we have a simple assignment. We need to complete the ranking without knowing what the word superior is. For the known sentences, like A is better than B, we can construct a kind of graph which says nodes indicates the products, arrow indicates the better product. So we don't know the meaning of two last sentences. But if we look at this graph and we look at the sentence, the first unknown sentence, A is superior to C, we can guess like A is better than B, B is better than C. By transitivity, probably A is better than C. If we can draw this line confidently enough, we can infer the meaning of the superior. And if we can infer the meaning of the superior, we can infer the meaning of the last sentence, which is D is superior to E, translates to the arrow pointing to D. By this, we can complete the full ranking. A is better than B, B is better than C, and so on. So this two problems. This shows that two problems. If we solve them together, we can actually improve both ranking of the entities and classifying, understanding the lexicon in which the sentence is written. These are two components, and we are going to model it in a probabilistic way. So here is we're taking apart all the complicated neural networks that we can't interpret, and we try to do it with using the probability models and simple feature engineering to make the model more interpretable. So the first part is about a competition model, which entity is better than the other entity or product. And the second part is about generating the words, essentially some kind of naive Bayes approach. How do we generate the words in a sentence given a certain class? The first part is related to competition model. Well, a competition model would describe a probability of winning for two players of winning in a particular game, in a particular match. So we have player A and G. They described by their latent scores, and we model the probability as a sigmoid function, which is indicated here as a difference of their latent scores. In this case, if the latent score of player A is much higher than AG, then the probability tends to go to 1, indicating that the player I is more likely to win in the game. So in our case, we have sentences, and we can consider the sentences as a competition between two entities, except that we don't know actually what the outcome is of comparison, and it actually depends on the on the way we write the sentence. So now, how do we write the sentence? We can observe two things here about the meaning of the sentence, essentially. The meaning of the sentence changes when the words are different, like better or worse. And the second, when the word order is different. So in this case, B is better than A is completely different from A is better than B. So this is a little bit different from sentence classification part, where we don't care about actually the position of the words in the sentence. So we're going to encode all the features like this. We're going to preserve the order of the words by indicating whether the word is in between two entities, or on the left part of the sentence or on the right part of the sentence. So intuition here is if we say A is better than B, we're probably going to hit this feature, which favors the first entity. Or I have a product A, but B is better, going to hit the favor to the second entity. Now, these two parts can be combined in a probability model like this. It's a graphical probability model, combining all the parameters together. So entity ranks for each entity, the comparison outcome for each sentence, then feature distribution for our naive Bayes classifier, indicating whether the first preferred entity, whether the first mentioned entity is preferred or the second. And then we observe the features in a way we encoded them, like #1 better, #2. So a little bit about the process in a more technical way. So it's a generative model, and we proceed to generate and describe the set of comparative sentences in the following way. So we essentially sample two word distributions, two feature distributions, then we indicate the rank for each entity, which we assume have no difference at the moment of generation. Then for each comparative sentence is going to move this rank towards minus, like minus infinity or infinity, depending on which entity is better, essentially ranking all the entities. For each sentence, we have a comparison outcome to sample, and then we have the features that compose the sentence. So this is a simple model of how people would come up with sentences for comparing entities. A little bit about experiments we've done. So we collected these comparative sentences and manually labeled them from Amazon on 4 different factors, on 4 different aspects like functionality, form factor, image quality, and price. So datasets are well, roughly balanced, so we use accuracy to indicate how good the model performs. So first is the interpretation of the sentences. So here we compare ourselves with simple classifiers that use these features that encode the word order. In this case, is naive Bayes or SVM model, and then compare gem is something that we propose that does two things together. Here we have good improvement in interpreting the sentences. So, but when we go to the level of ranking the sentences, we actually see that improvement is not that high. So, meaning that knowledge about some sentences allow us to understand how to rank entities. But, well, for interpretation, we need to learn a lot more lexicon to be able to interpret each sentence accurately. So, but essentially, two things modeling together improve both the ranking of the entities and the sentence classification part. So that's what I wanted to say about the text modeling, in particular comparative sentences. If you have questions now, I can answer. If you don't, then I'll give a word to back to Hady to describe the social network modeling approach.
Right, I think by now you get a certain theme that we are trying to look at different types of data and how we can actually extract preferences from them. Now the last one that we're going to talk about today is the social networks. Now we are talking here about like one format of data at a time. In the future, I think we are looking at richer models that try to pull them together. Now, but specifically for the social networks, the basic principle is the following. I mean, there is an English saying, right? Birds of a feather flock together. So things that are similar, they tend to be found together. Now, this is supposedly the Russian equivalent, right? The fishermen see other fishermen from afar. Now, this is based on some empirical analysis. It means there are previous studies that shows that indeed there is this correlation between people who are related to one another. This is a study that we did back in 2010. We are looking at LiveJournal data, for example. LiveJournal is like this blogging platform that used to be very popular in Russia. Now, this is based on a lot of users, like 200,000 users. Okay, so the idea then is to look at, is that really true that if you take any two people at random, how much common interest do they have? And if you take two people who are related socially, how many common interests do they have? And is it likely that if they are friends, then they will have more common interests? And it turns out that that is true, because most of the time we look at these are the random, these are the friends, and friends tend to have higher probability of having some number of common interests. And the correlation actually goes both ways, in the sense that if they have more common interests, they're also more likely to be friends. Now, we tried to exploit this and try to use it to learn about the preferences of users from the thinking that if I know something about your friends, I'm going to borrow something from them and try to predict something about you. So the model that we use to do this is another form of neural network. There is just like one key difference here. Now, initially, I think the previous example that we were showing in terms of neural network is what we call a feed-forward neural network, meaning that it goes in one direction from the input all the way to the output. Now, for some problems, like the problem that we are looking at now, it's not that there is input and output. It's more that we have made some observations. For example, the ratings that you have assigned in the past, and we would like to understand how to generate more observations. So it's not that to classify it, but we try to learn from the observations, try to generate more predictions in the future. Now, a model like that can be, in a simple way, can be modeled as what we call a generative neural network. And the basic idea is that the red colors, these are the observations. And we are trying to learn some hidden nodes, hidden neurons that can generate the observations. The thinking is that if I can generate what I observe, then the same parameter can generate future ones that I have not yet seen, and therefore I can make predictions. Now, this is called restricted Boltzmann machines. The word restricted there implies that the connections between hidden unit and visible unit, these are the only connections that are allowed. For example, you cannot connect the red ones to one another. You cannot connect the blue ones to one another. You can only connect blue to red, and so on. Now, this makes the inference simpler, because effectively the red one, the probability of generating one red node, is independent of all the other red nodes. So then that makes the inference easier. Now, this is essentially a formalization of this. And here the idea is that the X is the red, the H is the blue, and we need to learn some W, which is the weights that are in these connections. And the weights are going to be higher when you see a correlation between some visible unit and some hidden units. Now, these are all binary, so it's just zeros and ones. So when you buy something, it's a 1. When you don't buy it, it's a 0. So in this case, the hidden unit here is essentially going to be like a binary code, a binary vector, like 1, 0, 1, 1, 0, and so on, right? And each one is going to encode certain co-occurrence. Like, let's say if these two things are always brought together, so then this is, when this is a 1, then it's going to turn on 2 of them. So the thinking is that each of them is going to turn on different subsets of the items. Now, this is something that can be used for predicting the future adoptions. Now, we're going to talk a little bit about how we can use this in conjunction with the social networks. And so let's say the initial problem is that if I see one user, I look at all his previous purchases, then I can learn what binary pattern is going to encode his purchases. Now, but for different users, because they buy different things, then I'm going to end up with different binary codes. And now, if two users tend to buy the same things, they're going to share the same binary codes. So essentially, we are clustering users based on the different items that they bought in the past. So the way we can then encode social network, there are two ways. So one way, so one model that we call model 1 is like a wing model. And the thinking is the following. So let's imagine this is the binary code. Now, so if there is some binary code that predicts some adoptions, let's say in this case, the user bought 2 items. So people who have this code will buy these 2 items. Now, what we are going to do is to ask the model to use the same binary code to predict their friends. So here, let's say here, every node is a friend and is a 1 or 0, depending on whether they are actually friends or not. So let's say the same binary code is going to cluster users that buy the same things. Then that same binary code has to cluster users that tend to have the same friends. So here the underlying assumption is that if 2 people tend to buy the same things, they also tend to have the same friends. Now, of course, this is not always true of, in all cases, but it's true enough in many cases that it can improve the performance. But at the same time, this is also difficult for the model to learn, because essentially the model here has to encode both the social network and the adoptions or purchases at the same time. So then basically it makes it harder for the model to learn both of them at the same time. Whereas at the end of the day, what we're actually trying to do is not to predict your friends, we're actually trying to recommend you items to purchase. So that means that this is where the prediction space is. This doesn't really need to be predicted if we are not trying to recommend people who their friends are. So then we develop a different model, which is called model 2. Now the thinking now is different, right? So if you see this is the generative one. So that means this generates this generates this. So now here we are going to learn some binary pattern that will generate the adoptions. And what we have now is another layer of generative layer. But we encode the social network structure into this layer. So the thinking is that if, for example, 2 people, I only turn on a particular node if the user is friend with that node. So in this case, this user 1 is friend with himself, user 3 and user 4. So then when 2 different users are friends with the same people, we are going to turn on the same nodes. So then that forces them to share the same binary code, which will then generate the same predictions. So in this case, the model then doesn't need to learn the network structure. In fact, the network structure is encoded into the model itself. So then it just needs to generate the items. And indeed, it turns out that this actually makes the model perform better in terms of recommending the items to users. Now, we tried this on 2 different data sets. One is called Delicious. Delicious it's not about food. It's actually about bookmarking. So people go online and they bookmark different pages, but they can follow other people. So for example, if I follow you, it means that I like the things that you bookmark. I get to find out more about the things that you do. Now, Last.fm is a music service, so online radio. Again, the same thing. Like if I follow someone, then I get notified about the different things that the other user is listening to or is tagging. Now, this data has both social network as well as consumption data, so then we can use it to test the model. And we use recall here, recall meaning that how many items we can actually recall within the top 20 to top 200. Now, RBM is a basic model without the social network, so that's a blue color. If we use the model 1, which is the wing model, we get a performance improvement. But if we use the deep model, which is the model where we increase it by another layer, that achieves the best performance in terms of the green color. Now, one of the things that we do, yes.
Could you just tell more about this plot?
Yeah. So this is the, okay, so the M here is the top M, meaning that if I were to retrieve the top M items based on the highest probability of being generated by the model, how many of them are actually correct, meaning that I really observe them in the consumptions. Now, this is a recall. So now, the recall here, okay, so the part of the problem with recommendation research is that we only get to see what the user has adopted in the past. Now, one thing that we don't see, right, we cannot always say that it's wrong, meaning that if I don't see you reading something, it doesn't mean that you don't want to do it. It just means that, you know, maybe you have not come across it and so on. So most of the time we need to use recall, because the idea is that just because we have not observed you doing something, it doesn't mean that it's wrong. So that's why we don't rely on things like precision. So, yes. Numbers. You're saying, isn't this very small numbers? Yeah, okay. It is very small numbers. But even the best current models basically are operating at these small numbers. Now, for recommendation problems, generally the performance at this point of time is not very high. And part of the reason why it's not very high is because we are trying to validate based on past data. Meaning that, for example, right, what I want to know is that what you like. I can only test it based on the things that you bought in the past. But most of us have limited amount of money. We don't buy a lot of things. We may like a lot of things, but we don't buy all of them. So now, and so that's part of the problem. So that means when we evaluate, we can only evaluate based on things that we have seen you buying in the past. We don't know what you like. So that becomes an approximation. Now, the other thing also that we need to consider is that most of the recommendations online are actually low cost, meaning that I can show you things is for you to consider. That means if you don't buy them, that's fine too. That means that there is not much cost to the user, even if you show them a lot of, you know, so-called like not accurate things. But of course, over time you want to improve it, because at the end of the day, the user cannot possibly go through all the options. So, I mean, that's the basic idea. Yeah. So then we look at things more in relative form, how much we are improving upon the current baseline. And hopefully that is going to improve even more in the future. But the last thing that we want to test is the idea that, because whenever you absorb a new sort of information, we can't be sure that we are not just absorbing something that is random. For example, we use the social graph, but it's not clear, is the improvement coming just because we use a graph, any graph, or does it come from specifically the social graph? So one way we can test that is by testing the same model, but comparing two different graphs. One is a social network, the other one is a random network. But this is not just any random network. This is a network that has the same properties as the social network, meaning that every node has the same number of edges. So that means we keep that structural property, we just randomize the connections. So the thinking is that if it's all just because of the graph structure, then the random network and the social network should converge to the same performance. But they don't, because we see that there is a performance difference between the social network and the random network. So meaning that there is some information to the social connections. So that's one of the things that we learned. Now we did this for Last.fm. The numbers are higher, but still I think what we are looking for is the improvement, the relative improvement upon the base model, which is here. This is the model 1, this is the model 2. Now, that's essentially different parts of what we are going to be talking about today. Now, if you see, this is still kind of like a work in progress, because we have been looking at one modality at a time. And in fact, if you see, these are like different models. So we've been relying on some kind of neural network for images, a graphical model for text, and a different kind of neural network for social network. And I think trying to achieve something that is more integrated, more unified, that's where we are trying to go. Now, it's not always easy to do, because it turns out that sometimes different models work better for different kinds of data. So some of the promising directions include things like mixing these models together. So for example, you can have a model that has part of it being a form of neural network and another part of it being a form of a graphical model that somehow share the parameters. And these are some of the recent work that we are doing. Now, this is a slice of the things that we are doing with the objective of eventually building an end-to-end recommendation framework. And I think if you are interested, do let us know, and we'll see where we can go. And yeah, that's it for, yeah. I hope yeah, you learned something, and as much as we learned something from yeah. Any questions? Yeah. Yes, go ahead.
Thank you for the lecture and for the recent findings. I have two questions. One is kind of a small one, technical one. What were the features you have used in the first part you were talking about? What kind of items, features did you add at the last layer? I mean, just examples.
These are, so you're talking about the images part?
Yeah,
or
images and those items that were related to the restaurants.
So, in fact, at this time, for that specific work, we did not use any other features. So essentially, the only thing we use are the images themselves, and the supervision will be in terms of the labels, whether it's positive or negative, and that's all. That means that that's all what the models are based on. Then it tries to learn the mapping between certain visual features to the classification labels. Now later on, we add the identity of the restaurant, in the sense that every restaurant can have some parameters that are different. That means specific to that restaurant.
You mean the identity?
Yeah, identity. So it means that, but no other features in terms of where they are or what kind of food and so on.
Thank you. And one question is like on web mining in general.
Yes.
You've used delicious, and as far as I understand, you used only the social links there, right?
Only social links, right?
And I wonder, just from a legal point of view,
okay.
Is it okay to, or do you know of any examples of such things, to use some main text extraction from the web page algorithm, and to use the data posted on Delicious or Reddit from the data that users has posted and use them for NLP something?
Okay.
Whether it is legal or not.
Whether it is legal or not. Okay, so I think there is something, based on, I'm not a lawyer, right? So, but I think based on what I know is that there is something called fair use. And that generally means that, so I think one, there are some conditions to fair use. I think one is a proportion. That means that you don't reproduce everything. That's one thing. Like if you use like some relatively reasonable percentage of the data that you obtained publicly, and as far as possible when you crawl them, if we can, we try to respect, the robot.txt or any kind of constraint that, if we do those things, most of the time they are fine with it. Now, of course, I think when you republish the data, that's when I think it's a little bit tricky. I think doing research on them and publishing the results, because that's the results that you derive from it, I think that's fine, I think. Now, republishing the same data all over again, now that's, this one I'm not clear. And I guess I think if you don't reproduce the whole thing, I think that's probably still okay. Now, I kind of think that as long as it's a small scale, usually, and you don't benefit financially from it, they will probably leave you alone. Yeah, but as to whether it's legal or not, I will not comment specifically. Yeah.
So
but,
I'm not even sure that I get the question. So are you talking about whether it is legal to use some public information or what?
Whether it is okay. Well, say Delicious has links, right?
Yeah.
Some external hyperlinks to some.
Right.
And imagine the situation when you want to use the data which was not published by Delicious exactly, but the information that is beyond the links. So as to crawl some data from external various sources.
Oh, I see.
Yeah.
And well, with Facebook, for example, sometimes you can't.
Yeah.
Due to the rules, due to the.
But if you think about it, like Yandex or Google, they also crawl pretty much everything. But when they show you a snippet. To show the whole thing, you need to go to the original page. And I think that's one way they try to maintain this fair use limit. But I think if you're talking about research, right? Now, sometimes what we do to avoid these issues is to rely on data that is already there. That means we don't necessarily have to collect everything. Like Delicious and the Last.fm, these are actually benchmark data sets. I think they probably used it in some competition in the past for some conferences. So then we can reuse that. But we have crawled stuff as well. So I mean, that's, and I think we are not the only ones. I think generally for academic use, I would say doing something within certain limits are generally okay, especially if, we attribute it back to, wherever it is that we get it from. That's what I think. Yeah. I don't know. Do you have any comments, Maxim? Yeah.
It depends on the law of the country.
It could also be that, yeah.
Russia, it might be probably kind of, you can say that you use the data for research and it will be all right. So something like this.
Yeah.
One more question.
Yeah.
You said that you're going, you are moving towards using either a single model for multimodal data.
Yeah.
Maybe, which papers and which ideas do you think are more promising, the most promising now in the field?
So, okay, so I think when we talk about doing something that across modalities, like different modalities, you need bridges between the different modalities. Like, for example, it's not easy to find, like, for example, one single data set that has everything. And if there is such a data set, it's not easy to get them. So that means that, yeah. And even to try to build a model that does that, it's not easy, essentially. Now, what seems to be a promising approach, at least for us, because I think that's partly because where we are going, is that we've been using text as a kind of the stitch, like the things to combine things, because it turns out that, for example, if you look at a review system, right, like Yelp or any kind of restaurant reviews, this text is very informative, and then you can add some images that help to identify what part of the text are actually important. Then you can then go behind the text to see who is the user that has written that review. And increasingly, a lot of places actually has this social network element to it. Yelp does, so in that case you can follow people, so that if they are expert reviewers, you follow them. You get notified whenever they write a review, so that forms an approximation of a social network. Then that may be something that then you can put in as well. So far I think we have only been doing with, so this is essentially two things at a time, which is like image and maybe sentiment, text and maybe the comparisons, and social network as well as the adoptions. Yeah. Now, some of the current work that we are doing is to add one more thing. So for example, we had something that tries to do with a social network and text within a single model, or images and text within a single model. But there is some restrictions in terms of what we can model. So for example, if the images are using things like a neural network that are difficult to interpret and so on, sometimes for the text, then we have to somehow go into the same space. So then we may lose some of the advantages of the graphical model where things are still interpretable, because you can see the words and so on. Because by the time you come to neural networks, you don't know what's going on in between. Some input come in and some output go out. And yeah. Now there are a lot of work that talks about multimodality, but they tend to be like image captioning problems and so on. So I think it's helpful to look at those papers as well. But they tend to be the data tend to be much more controlled, because they tend to be data that has been manually inspected by people to make sure that the image and the caption are really very, very close. And whereas when we talk about web data, they tend to be noisier, dirtier, and that presents its own problems to it. Yeah, I don't know whether I'm answering your question properly, but yeah.
So if there are no other questions,
Yeah.
thank Hady and Maxime.